All right, now that we've looked at galvanic cells, let's take a look at determining how much electricity flows through when we're looking at these. So we're looking at now the electrochemical cells. And let's put a few kind of terms here. We're going to see that a voltaic cell is one that is spontaneous, meaning the reaction will happen as soon as we connect the circuit. Meaning as soon as the wires are in place, the electrodes are in place, the electrons will start to flow by themselves. On the other hand, we have the opposite, which is called an electrolytic cell, which is a non-spontaneous one. And in fact, for these to work, we have to apply external electricity. So we will artificially add electricity to the system to get them to happen because they are non-spontaneous reactions. And when we're looking at these, we're looking at a property called the electromotive force. Electromotive force. That means just how much force is generated by moving the electrons, or we might call it the voltage, which is a term that you might be more familiar with. Or you might call this the electric potential energy, or more commonly, potential difference. So what we're looking at is there's going to be some amount of electrons going through, and we're going to see that when we look at electricity, we're looking at voltage being joules per coulomb. Remember that coulomb refers to charge, so electrons have their charge. So we're going to see that that the energy and the charge are going to be related here, and that's going to be producing our voltage. So we're going to see that the biggest voltage comes with the fewest electrons being transferred with the more amount of energy per electron. So like whatever way of making this equation makes sense. We're not going to use the equation, but that's what we're looking at here. So we're looking at the joules per coulomb. So the energy per charge. That's our voltage here. And this is important for us because when we're talking about voltage, we're looking at the energy per charge, like we can say electron, because an electron is 10 to the minus 19 coulombs, but of 10 to the 19 electrons, we could say, however much energy is being transferred by those electrons, that's our voltage. So the more energy we can pack in, the better. And we're going to see that this depends on the reactions taking place in each half cell. We're going to see that the potential, which is given by E for your cell, will be related to the half reactions that are taking place. We're going to have the potential of the red cat cathode minus the potential for the anode. That's always how this the determination of this electromotive forces, or the voltage. We can call it cell potential, electric potential. There's a lot of different terms here. So your cell potential is related to the potential energy associated with your half reactions. Remember, the one at the cathode is your reduction, and your anode is the oxidation. So if we take a look at a particular reaction, which we've seen before, turns into copper 2 plus silver, we saw that the reduction is the silver, and the copper is the oxidation reaction. And what we'll do for this, in order to actually calculate the cell potential, we will go to our good friend Wikipedia, which has standard cell potentials for hundreds of reactions. Now, importantly, right in the middle here, we're going to see, right at 0, is what's called the standard hydrogen electrode. This is our reference point. Since these are all potential differences, the difference in voltage between two states, we have a standard 0 point. We're going to see things that are more positive are going to be more spontaneous, and ones that are more negative are going to be less spontaneous. I'm gonna sneeze. Excuse me. And we're going to see that these are all reduction reactions. They're all written as something plus electrons. And we're going to see here that we have that voltage, which is that cell, half cell potential. And we also see the number of electrons that are being transferred. We'll worry about that part later. Right now, let's focus on the voltage. So we're going to see here that some very non-spontaneous processes would be like lithium gaining an electron. Lithium does not want to be reduced. We're going to see negative is not good. We don't want negative potentials. So because lithium's reduction is very negative, just like with all of the reactions we've looked at before, if we flip that around, make it lithium becoming lithium ion plus electron, the oxidation reaction of this, well, that would be positive 3.04. So it becomes very favorable. So we're going to see that lithium, along with many of these very negative reduction potentials, are very strong reducing agents. I have to get that right. Reducing agents. They will get oxidized. So lithium is one of our strongest reducing agents. Because its reduction potential is so unfavorable, it's very likely to reduce something else instead. And on the other end of things, if we scroll all the way down to the positive side, I mean, these noble gases we don't typically see. Let's look at fluorine. This one's pretty common. We see that reducing fluorine, giving fluorine electrons, is very favorable. So fluorine is an excellent oxidizing agent. It wants to be reduced. We're going to want positive potentials because those are what are going to give us voltaic cells, ones that are spontaneous. So an excellent battery, we could say, would be made of fluorine and lithium, where the lithium is transferring its electrons to the fluorine. That would be extremely favorable. So, but that in mind, let's take a look at this particular one. When we're calculating the cell potential, we want to look at these standard potentials at the cathode and the anode. So if we want to look, our reduction reaction is silver ions turning into silver. So if we go back to Wikipedia here, I'm going to Control F and look for silver. Let's look up because there are like 30 of them here. But let's find silver have its ion turning into regular. Here it is right here. So silver metal plus the electron turning into, silver ion plus electron turning into silver metal. We have our cell potential is, I'm going to write this down, 0.7996. And now we want to look up the copper one. So I'm going to Control F for copper. We're going to have to find where our copper happens to be. That's copper 1. Aha, right up here is copper 2, turning into copper solid. These are always written as reductions, and that's okay. We're looking at right now technically the opposite reaction. That's fine, because this is our oxidation reaction anyway. But we still look it up as though it were a reduction. All of these are written as reductions, so that's important that we look those up. And we're going to leave this number alone. We're going to look it up. It's 0.337. So we found our reaction, even though it's the opposite one. These are always written as reductions. We found our second reaction. So, right, we know our half cells, or half reactions rather, are the following. Even though that second one was reversed on our table, we still use the value. You're not going to find anything else because they're all written as reduction reactions. So with that in mind, we have our reduction and oxidation now. So we can find the cell potential at standard conditions. We'll see that that will be our reduction, which is the silver, 0.7996 volts. minus 0.337 volts. Doing this math, calculator. 0.7996 minus 0.337 is 0.463, we'll say, volts. And that's a positive number. Often we will indicate the positive here. Even though typically in math and chemistry we don't indicate pluses, positive numbers, we will here for cells. One thing you might be asking is, well, hold up here. This silver has one electron, but the copper has 2 electrons. What's going on with that? Thankfully for us, and this is really kind of the only time in chemistry, we don't have to balance these. If we know our half reactions, we apply their cell potentials right off the table. The coefficient in your reaction has no bearing on your half cell potential. So that's important. So Ag plus E minus turning into silver has a half cell potential of 0.7996. If we have 200 silver ions plus 200 electrons turning into 200 silver, the potential is still exactly the same. The coefficients do not change your potential. That's very important here. Coefficients do not change the potential. So, lucky us, we don't have to worry about that. So you simply will take your reduction reaction, half cell potential, subtract your oxidation half cell potential, as written on the table. So don't be flipping signs. It's easier if you do it this way, trust me. If you try and look up oxidation values instead, and it's going to get confusing because all the signs are going to be different, trust me, it's a lot easier to look at it this way. So always consider it your reduction reaction minus your oxidation reaction. Find those on the table. Your oxidation reaction will always be written in reverse. So on this one, our reaction is the following. That's our copper turning into copper 2+. On the table, we look for the opposite of this. Look for reverse on the table. And use the number as written. Don't change anything. Otherwise, it'll make it more difficult. And so, this is going to be a voltaic cell. The reaction will happen instantly as soon as we connect it. And indeed, I'll put up a video where you can see the silver turning into silver solid and the copper forming nice, lovely blue copper ions. So, the last thing to note here is that these are standard. They're standard conditions, which means for solutions we have 1 molar concentration, 1 atmosphere of pressure, and 25 degrees Celsius. So those are our standard conditions. All right, I do want to mention as well that very positive ones, meaning those are good oxidizing agents, like fluorine, for example. If your cell potential is very negative, you are a good reducing agent. And in the next video, we'll take a look at some cells, and we'll be able to predict which one, if it's a voltaic cell, which one is going to be the one being reduced, which one is going to be the one being oxidized. So that'll be our next video.